Hello and welcome back to STEM Online Academy. My name is Jason Masterakos, for those of you who don't know. All right, let's get into it. Let's get right to the what's interesting today. We're going to talk about the Mobius function, but we're going to be talking about the infinite series of a Mobius function. So this will be very interesting. Okay, so I think you guys can all agree that with the fact that, to be honest with you for a second, most students, when they first see this type of series, right, this infinite series, okay, I'm zooming in on it right now, okay, the brain will shut down immediately. Okay, it looks intimidating. Okay, it looks random. It feels unfair, and it feels like one of those things you're just supposed to accept. You're supposed to accept that the infinite series is this. Okay, right? But here's the good news. This series is not about chaos. Okay. In fact, it cancels itself out for a very clean reason. Okay. And once once you see it, the confusion will completely disappear. Okay. So I want you guys to absorb this equation here. Okay. This equation. That's what we're going to be discussing in this video today. Okay. Now, in order for me to discuss this equation, I need to define the parameters and the variables, what means what. You obviously know what the capital summation is. What is mu of n? Okay, we need to discuss what mu of n is. I'm going to give a short definition, right? So just stay with me here. The good stuff is coming, but I first need to define what mu of n is in the series in order for us to understand where to go from here. Okay, so here's the definition. Okay, for every positive integer called little n, I'll call little n. Let's define the little Greek letter mi of n as the sum, right? So this is the sum of all primitive nth roots, okay? And it has values uh, the values are actually mapping, right? They're mapping from the natural numbers to this set here. Okay, let me explain. The set is -1, comma 0, comma 1. Okay, so again, the set goes from the natural numbers, okay, maps to the set -1, comma 0, comma -1. Okay, right? So depending on the factorization of n, okay, into the prime factors, okay, so mi of n is the piecewise, we say it's piecewise to some degree, where we have 0 if n has one or more repeated prime factors. Okay, again, if n has one or more repeated prime factors, that's case 1. Case 2 now is when we have 1 if n is 1. Okay, and then the last case, -1 to the k if n is a product of k. Okay, of k distinct primes, right? Different primes. So it has to be a product of k distinct primes to have -1 to the k. Okay, so I hope that defines what mu of n is in our infinite series. Okay, so let's continue with this infinite series here. Okay, the problem is simple to state. What happens to this sum? Okay, what happens to our infinite summation when mu of n is the Mobius function? Okay, so we're not exactly trying to prove a theorem in this case, in this video, not memorizing any facts. We just want to understand why this series vanishes. That's the point of this video, is to why this series vanishes. Okay? And if you've ever felt like this is an application of calculus to number theory, by the way. Yeah, if you ever felt that number theory is just a pile of strange definitions, I want you to know that it's not your fault necessarily. Okay? It's not your fault at all. Okay? The structure is just purely hidden. Okay? And our job is going to uncover it. Okay? So that's exactly what we're going to do. Right? So let me go to the struggle when it comes to this series, actually. Okay, let's go to another page. Okay, just give me a moment. We're going to talk about the struggle. The struggle. And when I mean struggle, the struggle that students have, whether you're a student, whether you're whatever, it doesn't matter. When people come across this, this series becomes a bit problematic, as I mentioned on the first page. Okay, all right, just give me one moment. So the struggle. So this is where students get stuck, right? Right. I'm going to emphasize here, students get stuck with all the following. Okay, with 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 the following. Okay, here's what they get stuck with. Okay, they get stuck with the following. They compute partial sums. Okay, so they think they need to compute compute partial sums. Compute partial sums. Partial sums. Okay. They see numbers jumping around. Numbers jumping around, if that makes sense. Around. And then finally, uh, positive and negative, no clear pattern. Okay, so positive, and negative, negative. There's no clear pattern to the series. So that's what makes this series difficult. Clear pattern. Okay, clear pattern. I will admit myself, when I was going through it myself, this particular series before, uh, give me a hard time. At first, it took me a while to get it actually to intuitively understand how this series works. So I myself had difficulty with this series. It took a while for me to get it, but now I want to share what I figured out. Uh, my way of learning it in a very productive way for you to be able to learn it. Okay, if that all right. So back to what I was saying. And most people think there's no way that this can be controlled, right? That this particular series can be controlled whatsoever, right? But that feeling, that frustration comes from using the wrong mental model. That's my point, okay? Not the calculation part of it, but the wrong mental model of how to approach the reasoning of this series, okay? This series is not random noise. I'm not going back and forth, right? So, series is not random noise. Okay, it's just organized cancellation. That's my point here. Okay, right, and I'm gonna discuss this in a more interesting manner. Actually, I'm gonna pull up a simulation, a mathematical simulation that I made here. Okay, so let's go to the desktop, and we're going to look at the simulation. Okay, so you see the Mobius function here, right? Now let's slow this down and remove the any type of mystery that's going on, right? You'll notice that the Mobius function uh, doesn't measure any form of size. Okay, doesn't measure the size, and it doesn't measure growth. Okay, just pay attention to the model there. Okay, what it's measuring is a form of prime structure with the prime numbers here. Okay, now specifically when you have little Greek letter me, right? Me of n as a function of n. When me of n is equal to 0, you're going to notice something here. Okay, so what's happening when me of n is equal to 0? If n has a squared prime factor, That's exactly what's happening. So when me of n is 0, what ends up happening is that if n has a square prime factor, that's case 1. Okay, and you'll notice it on the model here as well. Okay. Then you'll notice case 2, that me of n is equal to 1 if n is a product of any even number of distinct primes. Okay. So that's case number 2, right? And then you'll notice with case 3 here, okay, I'm just going to rewind. Case 3 is that when me of n is equal to -1 if it's an odd number. Okay, so there's 3 cases to this model here that I've mentioned. Okay. Also, tell me what you think about the model once I've uploaded this in in the YouTube video in the chat below. Would appreciate it. If I need to work on something, please let me know if I need to make it better. Okay, so again, if me of n is equal to 0, if n has a squared prime factor, when me of n equals 1, that's if n is a product of an even number of distinct primes. And number 3, case 3, me of n is equal to -1 if it's an odd number. Okay. So already most numbers don't even participate in this sum. That's what makes this sum bizarre. Okay. Most numbers are not within this summation. That's the first cancellation. Okay. And the numbers that do participate come in balanced pairs. Okay, so let's get out of the model and go back to the whiteboard. Okay. All right. So let's continue. Now, I'm going to talk about, when it comes to me event and the series in general, why randomness is wrong. Okay. Why randomness. Might use another page specifically to discuss randomness. Okay. So why randomness is the wrong idea. Okay. So why, okay, randomness, randomness is, that there is wrong. Is wrong. Okay, so why randomness in particular is wrong for evaluating this series. Okay, we're going to talk about that. Okay, just give me a sec. Let me just highlight this. Here's the idea I want you to remember. Okay, here's the key idea. The idea is that multiplicative, right? So here's the key idea. Here, key idea. Okay, idea. Okay, key idea. The key idea is that multiplicative structure, okay, I'm going to put here, is that multiplicative structure beats randomness. Beats randomness. Okay, randomness. Okay, beats randomness. All right. All right. So it beats randomness, and the Mobius function is multiplicative. Okay, so and so I want to let you know the Mobius function is a multiplicative function. Okay, if you look back again at the Mobius function here, it's multiplicative. It's actually a multiplicative function. Okay. All right. So it's a multiplicative function. And that means its behavior, okay, is this dictated by primes, not by chance. Okay. So multiplicative structure, might just add these as points, multiplicative structure. Another thing is that the Mobius function, Mobius function is multiplicative Time to get a new pen. Sorry, but I hope you can read my writing. Multiplicative. Okay. Is multiplicative. Okay. And when you divide by n, you're not amplifying the noise. Okay. You're going to be weighting terms so that positive and negative contributions are naturally going to offset each other. Okay. So another thing too, uh, when it comes to the Mobius function, right? Uh, its behavior is dictated by primes. Its behavior is dictated. Behavior. That's why I should put down. Behavior is dictated by primes. Right. So its behavior has to be dictated by prime numbers. Okay, so multiplicative structure beats randomness. Mobius function is multiplicative, and its behavior is dictated purely by prime numbers. Okay, so this is um, so this is not luck. This is just purely a structural architecture that I'm talking about of the Mobius function. Okay, now let's talk about the core insight. Okay, let's talk about the core insight. Right, let's talk about the core, the core insight. Okay. All right. Actually, I might make this bigger. Let's talk about the core insight. The core insight of this uh, conceptual problem. Okay. Now, here's the heart of the explanation when it comes to this series. And this is where things usually click for most people. Okay. This is the way I best try to describe the Mobius series, Mobius function in my own words. Okay. You will notice that the Mobius function, right, can be written as the inverse of a Riemann zeta function. Okay, so let me just write here. Okay, I'm going to put this over here. That 1 all over zeta, that's a zeta, by the way. Zeta is a function of s, okay, is equivalent, right, to the summation from n equals 1 to infinity of the Mobius function u of n divided by n to the power of s. Okay, where s has to be strictly greater than 1. Okay, so what does that mean intuitively? I said how the Mobius function, uh, the infinite series of the Mobius function, sorry, is equivalent to the Dirichlet series. Okay, so what does that mean intuitively? What does it mean? What's the point of this equation? We have to understand what it means. Okay, and that's usually why my channel is about um, mainly about getting directly to the concepts, because quite often in mathematics people don't understand what on earth it means. Okay, so it means the Mobius function is undoing multiplicative buildup. Okay, so it's the inverse of accumulation. Okay, so not accumulation but the inverse of accumulation. So when we approach s equals 1, the series doesn't explode, it collapses. Okay, and I think my model was showing you that there was some sort of, you can see how the graph was behaving, right? That's why the sum doesn't grow, it just cancels. Okay, right? So I think you can agree that this gives a better in-depth understanding of the Mobius function as an infinite series. Next is another thing that's very important is why the sum wants to be 0. Okay, why this sum here goes to zero. It actually does. Okay. Why the sum goes to zero? Well, that's not quite the right emotional picture. The truth is more subtle, actually, and more beautiful. Math is beautiful, right? It is, because you're making order out of all the chaos. The sum wants to be zero, right? Not because every term vanishes per se, okay? It's because of the fact that the structure is forcing a balance, okay? All right. So this is the same idea behind, for instance, I've talked about applications of calculus before, but to different things. Today is number theory, but another time I've talked about, calculus being applied to signal cancellation in Fourier transforms and stuff like that. Noise suppression in physics. When it comes to noise, I mean mainly like any type of musical type of instrument. Okay, and finally, destructive interference when it comes to waves. Okay. Yes. Very interesting stuff. So there's a lot of applications of calculus to number theory, to physics, and to anything else, right? Right. So number theory is just doing the same thing quietly. That's what number theory is. Okay. Right. And I think all of this is explaining that in a more conceptualized view. Okay. So what this teaches you about math? Okay. What does this teach you about math? That's a question that we have to answer. Okay? If this series ever made you feel behind or inadequate, let me say something very clearly that I want to bring to light here is that you're never supposed to attack it using brute force, logical rigor. Okay, but you are supposed to see structure first. Sorry, that's what I'm trying to say. You want to see the structure first. Okay. So mathematics is not about surviving the chaos. It's about recognizing when chaos is an illusion. As I said, creating order out of the chaos. Okay, and this way of thinking, looking for cancellation, symmetry, and architecture is exactly what strong mathematicians and theoretical scientists do instinctively, right? When they want to understand how nature works. Okay, all right. Just take a moment and absorb that series. That's a nice series. You have to agree, right? Um, so if you want to train this kind of thinking, not memorization, no tricks, and no bullshit whatsoever. Okay, I've written a book called Advanced Integration Techniques, which is brought to you in part by uh, my company STEM Online Academy. All right, advanced integration techniques that's built around structure first, right? Structure first, problem solving. Okay, so that'll be in the description below after this YouTube pre-recording. It'll be in the description below. And if you're stuck in any of the courses of analysis slash calculus, ordinary differential equations, or even I also teach physics as well at the undergraduate level. I also offer one-on-one coaching slash tutoring focused on clarity, right? Again, clarity and not speed. Okay, because you have to understand it first before you can go through it fast, right? Speed is something. There'll be a link to the description in the description below for this YouTube video. All links will be below. Okay, so again, all links will be below. If you're interested in learning this type of way of thinking. Okay, if you have any questions, you can contact me. Okay, and remember one thing: difficulty um, doesn't mean you don't belong. It usually means you're right at the edge of understanding. Okay. In other words, my point is you have to struggle with the problems. Okay. And I mean struggle by yourself, right? Yes, That's annoying, but there's no fast way to do it mathematics. Okay, you have to actually struggle with the problems. Okay, but trust me, I know what I'm talking about. It means you're at the edge of actually conceptually understanding the concept. Okay, thanks for watching, and if this helped, please consider like and subscribing. This channel is about making hard ideas feel human again. Again, right? Making hard ideas feel human again. I'll see you in the next problem um, on Thursday. All right. Bye for now.